Gazing up at the night sky, you might see only darkness punctuated by distant stars, but that emptiness is an illusion. What looks like nothing is actually a vast, swirling ocean of gas, dust, and energy, a cosmic tapestry so rich and mysterious that scientists call it the interstellar medium. This isn't just empty space, it's the hidden stage where stars are born, where galaxies evolve, and where some of the universe's most baffling secrets whisper to us from the void. Think of it like the air between us, invisible yet everywhere, shaping everything. Only here, the secrets it holds are stranger than anything we could dream up. The interstellar medium is more than just the backdrop of the cosmos, it's alive with riddles. Floating within it are ghostly molecules that shouldn't exist, radiation with no clear source, and structures so enormous they defy logic. Somewhere in that haze between the stars, there are forces at work we don't yet understand, clues to questions we haven't even learned to ask. Why does certain space dust glow with impossible energy? What causes those eerie, unexplained radio signals? And could this cosmic fog hold the key to how life itself began? That's exactly what we're diving into today, 25 of the most astonishing mysteries hidden in the interstellar medium. From colossal magnetic filaments stretching across light years to the bizarre chemistry of distant nebulae, these aren't just scientific curiosities, they're pieces of a puzzle that could rewrite our understanding of the universe. So let's peel back the veil on this cosmic frontier together, because out there in the spaces between the stars, the universe is telling us a story, and we're just beginning to listen. Hidden deep within the interstellar medium, there are regions so dense and cold they swallow light itself, dark molecular clouds. These cosmic vaults are where new stars take shape, yet we can barely see inside them. Picture trying to watch a snowstorm through a blackout curtain. That's how effectively these clouds cloak their secrets. Their thick veils of dust and gas block nearly all visible light, leaving astronomers to piece together their mysteries using only faint whispers of radio waves and infrared signals. What makes these clouds even more baffling is their defiance of our expectations. According to traditional models, such dense pockets of matter should collapse under their own gravity, sparking star birth at a predictable rate. But these cosmic nurseries operate on their own enigmatic schedule. Some regions remain eerily dormant, while others erupt with sudden bursts of stellar activity, as if flicked by an unseen switch. Then there's the question of what they're made of. We've detected molecules in these clouds that shouldn't survive the harsh conditions of space, complex organic compounds clinging to dust grains like frost on a window. How do these delicate structures form in an environment so cold it's barely above absolute zero? Some scientists speculate these clouds could be chemical factories, brewing the building blocks of life long before planets even exist. But perhaps the most haunting puzzle is their scale. These clouds can stretch for dozens of light years, yet their interiors are so still and frozen that time seems to pause. Within them, gravity plays a slow, silent game, pulling matter together over millions of years until somehow, unpredictably, it ignites. Until then, the dark molecular clouds keep their secrets locked away, reminding us that even in the vastness of space, some things remain just out of sight. While the dark molecular clouds hide ancient secrets of star formation, another enigma races toward us at nearly the speed of light, cosmic rays. These aren't beams of light, but invisible bullets of energy, subatomic particles accelerated to unimaginable speeds somewhere in the depths of space. Every second, thousands of them pierce through your body without a trace, yet we still don't fully understand where they get their staggering power. The mystery begins with their acceleration. Some cosmic rays pack more energy than the most advanced particle colliders on Earth, as if nature has built a hidden supercharger in the cosmos. Supernova, the explosive deaths of massive stars, are prime suspects, their shockwaves acting like cosmic slingshots. But here's the catch. Even the mightiest supernova can't explain the most extreme particles we've detected. Some arrive with energies so high, they must have been flung across the universe by something far more violent, like merging black holes or active galactic nuclei. Yet when we trace their paths back, the trails often vanish into darkness. Then there's the puzzle known as the knee and ankle rod bends in the cosmic ray energy spectrum that defy explanation. Below the knee, particles behave as expected, their numbers dropping as energy increases, but above it, the rules change. Fewer particles reach these ultra-high energies than our models predict, as if an invisible filter blocks their journey. The ankle is even stranger, a point where the trend reverses, and the highest energy particles become slightly more common again. It's as if the universe has dials it keeps tweaking, and we're only now noticing the settings. What's tantalizing is that these rays might carry fingerprints of their origins. Some contain rare elements like lithium and boron, forged in stellar furnaces or perhaps even more exotic environments. Others hint at interactions with the interstellar medium itself, their paths scrambled by magnetic fields we've yet to map. Unraveling these clues could rewrite not just astrophysics, but our understanding of how energy flows through the cosmos. For now, though, the question remains, what cosmic engines are powerful enough to launch matter across the universe like this? The answer is still racing toward us, hidden in those silent, speeding particles. If the universe were a grand accounting ledger, we'd have a serious discrepancy. Half of all normal matter has gone missing. Not dark matter or exotic particles, but the ordinary stuff that makes up stars, planets, and even us, baryons. They should be everywhere, yet when we tally them up, the numbers don't add up. This is the missing baryon problem, one of the most persistent puzzles in modern astrophysics. Unsurprisingly, the interstellar medium might be hiding the receipts. For decades, astronomers assumed this lost matter was scattered in the vast voids between galaxies, but spotting it was like trying to find smoke in a pitch-black room. Then came the theory of the cosmic web, a sprawling, invisible network of filaments that connects galaxies like threads in a tapestry. These filaments, made of superheated gas, could be the hiding place for those missing baryons. The catch, this gas isn't just hot, it's warm hot, a diffuse plasma too faint to glow like a star but too energetic to cool down. Scientists call it the warm-hot intergalactic medium, or WIM, and it's been devilishly hard to detect. Recent breakthroughs, though, have given us glimpses. Telescopes tuned to X-ray and ultraviolet wavelengths have caught faint absorption lines in the light of distant quasars, tiny dips in brightness caused when WIM gas absorbs specific wavelengths. It's like finding fingerprints on a window pane, proof someone was there. Even more convincing are observations of the Sunyaev-Zeldovich effect, where this elusive gas distorts the cosmic microwave background, leaving faint wrinkles in the afterglow of the Big Bang. But the plot thickens. Some of these baryons might not just be in intergalactic space, they could be lurking right in our galactic backyard, woven into the interstellar medium itself. Ultraviolet telescopes have spotted patches of ionized oxygen in our galaxy's diffuse gas clouds, hinting at reservoirs of hidden matter. If confirmed, it would mean the ISM isn't just a stage for star formation. It's also a cosmic vault, quietly hoarding a chunk of the universe's missing inventory. The implications stretch beyond bookkeeping. If baryons are tied up in these hard-to-detect states, it could reshape how we understand the evolution of galaxies. After all, this missing matter fuels star birth, drives chemical enrichment, and could even dictate the fate of entire galactic neighborhoods. For now, the hunt continues, one faint signal, one quasar's flicker at a time. Because somewhere in that haze between the stars, the universe's ledger might finally balance. Rising above and below the Milky Way's disk like twin volcanoes, the Fermi Bubbles stretch 50,000 light-years into space cosmic geysers spewing unimaginable energy. These gargantuan structures, discovered only in 2010, glow faintly in gamma rays, revealing a violent outburst from our galaxy's core. But here's the twist: no one knows exactly what eruption carved them. It's as if the Milky Way burped and left behind a mystery spanning half its width. The leading suspects: our galaxy's supermassive black hole, Sagittarius a star, and a frenzy of star births. Black holes are notorious for their chaotic appetites when they feed. They can eject jets of plasma at near-light speeds. Perhaps a long-ago feast sent shockwaves rippling through the galactic halo, inflating these bubbles like balloon animals. Yet curiously, the bubble's energy signature doesn't quite match typical black hole outbursts. Their gamma-ray glow is smoother, more uniform, lacking the telltale spikes of a recent black hole tantrum. That's where the star formation theory enters. Imagine thousands of supernovae exploding in concert near the galactic center. Their combined winds could theoretically blow gas outward, sculpting these colossal structures. But again, the math stumbles. The energy required exceeds anything observed in even the most active star-forming regions. It's like trying to power a city with a single wind turbine. The scale just doesn't compute. What really baffles astronomers are the bubble's sheer longevity. If they're millions of years old, why haven't they dissipated? Their crisp edges suggest ongoing energy input, as if some unseen hand keeps topping them up. Even stranger, similar structures appear in other galaxies, hinting at a universal phenomenon we've barely begun to decode. One provocative idea ties it all together. What if both theories are right? Perhaps black hole activity and starbursts collaborate in ways we've yet to model, their combined forces creating something greater than the sum of their parts. Until we peer deeper into the galaxy's stormy core, these geysers will keep challenging our understanding of how galaxies live, breathe, and occasionally erupt. Starlight carries hidden messages from across the galaxy, but some of them remain unread. When astronomers split that light into rainbows of color, certain wavelengths go mysteriously dark, as if something out there is selectively absorbing them. These are the diffuse interstellar bands, over 400 unexplained absorption lines that show up in nearly every direction we look. For a century, they've resisted every attempt at decoding, earning the title of spectroscopy's oldest unsolved puzzle. What makes these bands so stubborn? First, their sheer variety. Unlike the crisp fingerprints of simple molecules, these absorptions are broad and smeared, hinting at something more complex, perhaps vast clouds of tangled molecules or unusual chemical structures we've never encountered on Earth. Early hopes pinned them on polyaromatic hydrocarbons, those flat, carbon-rich molecules found in soot and cosmic dust. Yet lab tests show pHs can't explain all the bands, leaving glaring gaps in the theory. Then there's their persistence. No matter where we look, whether through dense molecular clouds or the diffuse emptiness between stars, these bands appear with eerie consistency. It's as if the entire galaxy is laced with the same mysterious substance, something that doesn't behave like any known molecule. Some researchers suspect we're dealing with entirely new classes of matter, fragmented graphene flakes, warped carbon cages, or even molecules stabilized by the unique conditions of space that would crumble instantly on Earth. The real frustration lies in the clues themselves. The bands aren't random, they follow patterns, grouping in families that suggest shared origins. But without matching them to lab-created compounds, they're like an alphabet where we know the letters but not the language. Recent experiments with ionized fullerenes and carbon chains have shown promise, yet the full picture remains just out of reach. What's at stake isn't just solving a cosmic riddle. These absorbing molecules could be vital threads in the story of how complex chemistry spreads through galaxies, seeding the raw materials for planets and perhaps life. Until we crack their code, a fundamental piece of the interstellar medium's recipe stays locked away, written in light we can see but still can't understand. Hydrogen, the universe's simplest and most abundant element, has a voice, and it sings at a wavelength of 21 centimeters. This faint radio whisper, produced when hydrogen atoms flip their electron spins, has been astronomy's workhorse for decades, mapping the Milky Way's spiral arms and peering into the cosmic dark ages. But lately, this reliable signal has started behaving strangely, revealing holes in our understanding of the interstellar medium's most basic ingredient. Take the variations in its intensity. Across different regions of space, the 21-centimeter line fluctuates more than our models predict, as if invisible hands are tuning the volume knob of the cosmos. Some patches of hydrogen glow brighter, others dimmer, with no obvious correlation to density or temperature. One tantalizing explanation: dark matter might be meddling. Certain theoretical particles, like weakly interacting massive particles or actions, could subtly interact with hydrogen, sapping or boosting its signal in ways we're only beginning to simulate. Imagine dark matter as a cosmic DJ, remixing the hydrogen line's output, except we're still deciphering the playlist. Then there's the bombshell from the experiment to detect the global epoch of reionization signature, or edges. In 2018, this small radio antenna in the Australian outback picked up a 21-centimeter signal from the universe's infancy, a time nicknamed the Cosmic Dawn. But the signal was far stronger and colder than anyone anticipated, as if the primordial hydrogen had been chilled by something exotic. The implications shattered expectations. Either our models of the early universe's thermodynamics are wildly off, or something unknown was absorbing heat from that ancient gas. Proposed fixes range from novel dark matter interactions to unexpected radiation from the first stars. But with no consensus, the EDGE's result remains a glowing question mark. What's thrilling is how these anomalies intersect. If dark matter can explain both the EDGE's signal and modern hydrogen quirks, it would mean the interstellar medium isn't just a passive backdrop. It's a dynamic arena where ordinary and dark matter dance in ways we've yet to decode. For now, radio telescopes worldwide are tuning in, listening for hydrogen's faint song to reveal its next verse, because every unexpected dip or peak in that 21-centimeter line might be a clue not just about the gas between the stars, but about the universe's hidden architects. Interstellar dust should be, by all accounts, the universe's tiny, jagged fragments of rock and carbon, the crushed remains of dead stars. But when astronomers finally got a close look at these cosmic grains, they were met with a shock. These particles aren't rough or chaotic. They're smoother than polished glass, larger than anyone predicted, and so abundant they're bending our understanding of how matter coagulates in space. It's like expecting a pile of shattered bricks and finding a beach of perfectly rounded pebbles instead. The first clue something was off came from starlight itself. When light passes through dust clouds, the way it scatters reveals the grain's size and texture. Instead of the expected fine mist of nanometer-scale particles, observations pointed to grains stretching up to a micrometer, 1,000 times larger than early models suggested. Even more baffling, their surfaces lacked the craggy, irregular shapes seen in lab simulations of interstellar chemistry. How could something forged in the violent deaths of stars and battered by cosmic rays end up so unnaturally smooth? One theory points to cosmic ice. In the frigid depths of molecular clouds, dust grains become encased in layers of frozen water, methane, and ammonia. Over millennia, gentle collisions might sand these icy mantles down like rocks tumbling in a stream, but this doesn't fully explain the sheer size of the grains. Another idea involves sticky carbon coatings, molecules that act like cosmic Velcro, helping grains clump together into larger, more spherical shapes. Yet lab experiments struggle to replicate the efficiency needed to match what we see in space. Then there's their staggering abundance. These dust grains are so widespread, they blot out entire galaxies from our view, masking cosmic events behind curtains of opacity. In some regions, there's so much dust that it absorbs half the starlight trying to pass through. This creates a paradox. If dust forms primarily from supernova explosions and stellar winds, there shouldn't be nearly enough to account for the numbers we observe. Some hidden process must be churning out dust at an astonishing rate, possibly in the gentle outflows of aging stars or even in the turbulent disks of newborn planetary systems. Perhaps the most tantalizing clue lies in their composition. Spectral analysis reveals signatures of silicates, graphite, and even organic compounds materials that shouldn't coexist peacefully under the same conditions. It's as if the universe has multiple assembly lines for dust, each operating under different rules. Could these grains be the universe's way of recycling matter, breaking down and rebuilding itself in cycles we're only beginning to trace? For now, every answer raises new questions. These deceptively simple specks are more than just cosmic clutter. They're the hidden architects of the galaxy, shaping how light travels, how stars form, and perhaps even how planets gather their raw materials. Until we unravel their secrets, the interstellar medium's dust will keep obscuring more than just starlight. It'll keep hiding the truth about how our universe builds itself from the ground up. The interstellar medium isn't just a soup of gas and dust. It's threaded with invisible forces that sculpt the cosmos on a vast scale. These are the magnetic fields, ghostly tendrils of energy stretching between stars, so powerful they can steer entire galaxies, yet so delicate we can barely detect them. Unlike the clean lines of a bar magnet, these fields twist into chaotic, fractal-like webs, turning regions of space into cosmic labyrinths where matter dances to an unseen rhythm. One of their most startling effects, they're the universe's ultimate puppet masters when it comes to star formation. Picture a collapsing cloud of gas ready to ignite into a new star. Without magnetic fields, gravity would crush it instantly into a fiery ball. But the fields resist, pushing back like an invisible hand, slowing the collapse and stretching the process over millions of years. In some cases, they even channel the gas into spiraling streams, shaping the birth of solar systems before the first light flickers on. Yet sometimes, they do the opposite, intensifying the collapse by trapping gas in magnetic knots, triggering explosive bursts of star birth. Why they switch between these roles remains one of astrophysics' great unknowns. Mapping these fields is like trying to trace the path of a shadow. Astronomers use polarized starlight, studying how dust grains align with magnetic lines like cosmic compass needles. But the fields refuse to sit still. Turbulence from supernova, stellar winds, and even galactic rotation twists them into bizarre configurations. Some regions stretch taut like guitar strings, others crumpled into chaotic tangles. The most baffling feature, their fractal nature. Zoom in on any section and you'll find the same intricate patterns repeating, as if the universe stamped them with a hidden blueprint. The real mystery lies in their origins. Are these fields primordial, woven into the fabric of space during the Big Bang? Or are they forged anew in the hearts of galaxies, amplified by the churning dynamo of interstellar plasma? Some theories even suggest they're self-replicating, growing stronger as they interact with cosmic rays and ionized gas. Whatever the truth, one thing's certain: without these invisible architects, the interstellar medium and the stars it births would look utterly unrecognizable. What's tantalizing is that these fields might hold the key to another puzzle: how energy travels across the galaxy. Cosmic rays, those high-energy particles streaking through space, don't move in straight lines. They spiral along magnetic field lines like cars on a twisty racetrack. Could these hidden structures explain why some rays arrive with unexpected energies or directions? Until we decode their maps, we're missing a fundamental layer of how the universe moves, breathes, and builds. For now, these phantom forces keep their secrets, leaving us to trace their influence one indirect clue at a time. Deep in the cosmic void, floating like glowing islands in a sea of darkness, there are structures so massive they dwarf entire galaxies, Lyman alpha blobs. These eerie, diffuse clouds of hydrogen stretch for hundreds of thousands of light years, pulsing with ultraviolet light as they drift through deep space. The strangest part, they shouldn't glow this brightly. Hydrogen gas emits light only under very specific conditions, usually when blasted by intense radiation or heated by violent events. Yet these blobs shine with the luminosity of billions of suns, their energy sources completely hidden from view. One leading theory points to quasars, the blazing cores of distant galaxies powered by ravenous supermassive black holes. Perhaps these cosmic beacons flood nearby hydrogen with so much energy, it fluoresces like a neon sign. But here's the catch: while some blobs sit close to quasars, others float in perfect isolation, glowing defiantly with no obvious power source. If quasars light them up, why do some blaze independently like campfires with no match? Then there's the star formation hypothesis. Imagine entire galaxies drowned in their own birth gas, pumping out stars at a rate hundreds of times faster than the Milky Way. The combined ultraviolet glare from these stellar nurseries could theoretically illuminate the surrounding hydrogen. Yet when astronomers peer into some blobs, they find far fewer stars than needed to explain the glow. It's like stumbling upon a forest where every leaf shines, but there are barely any trees. The most puzzling explanation involves something called cold accretion, a slow, quiet process where hydrogen gas trickles into galaxies along vast cosmic filaments. As this gas falls inward, friction might heat it just enough to produce that telltale Lyman alpha glow. But models suggest this should be a faint, localized process, not the colossal fireworks we observe. How could such a gentle mechanism light up structures large enough to swallow galaxy clusters? What makes these blobs truly mind-bending is their structure. They're not smooth or uniform, but filamentary, with glowing tendrils weaving through them like veins in a leaf. Some even appear hollow, their light concentrated in delicate, bubble-like shells. This suggests something dynamic is shaping them, perhaps galactic winds carving cavities, or shock waves rippling through the gas. The implications stretch beyond the blobs themselves. If cold accretion really can power them, it would mean galaxies grow not just through violent collisions, but by sipping quietly from the cosmos' hidden rivers. And if quasars or star formation are responsible, it challenges our understanding of how energy spreads across intergalactic space. Either way, these glowing giants are forcing us to rethink one of astronomy's oldest questions: what lights up the universe? For now, the Lyman alpha blobs keep their secrets, shining silently in the dark, waiting for us to decode their radiance. Some galaxies defy every expectation: great, sprawling islands of stars that drift through space almost unseen. These are the ultra-diffuse galaxies, cosmic phantoms as large as the Milky Way, but with stars so thinly scattered they're nearly transparent. But their most baffling feature isn't their faintness, it's what's missing. Unlike normal galaxies, which brim with the interstellar medium's gas and dust, these ghostly giants appear almost empty. Take Dragonfly 44, a galaxy with 1% the Milky Way's mass but roughly the same width. It should be drowning in interstellar gas, yet scans reveal barely a wisp. Where did it all go? The first clue lies in their environments. Many ultra-diffuse galaxies orbit near massive galaxy clusters, where gravitational tides and superheated plasma act like cosmic sandblasters. As these galaxies swing through these violent regions, their gas could be torn away in a process called ram pressure stripping. Picture a dandelion puff caught in a gust, delicate filaments ripped loose, leaving only the barest skeleton behind. But here's the twist: some of these galaxies float in quiet voids, far from any disruptive neighbors. If they weren't stripped, why do they lack the interstellar medium's signature glow? That's where dark matter enters, or rather, fails to. Most galaxies are cocooned in vast halos of this invisible substance, whose gravity corrals gas into star-forming clouds. Yet measurements of Dragonfly 44 and its kin reveal a shocking deficit. Their dark matter halos are either unusually diffuse or oddly misaligned, leaving their gas unattended and vulnerable. Without that gravitational anchor, even modest stellar winds or supernova shocks could blow their interstellar medium clean away like dust scattered by a weak breeze. But the plot thickens when we consider their star-forming history. Ultra-diffuse galaxies aren't just gas-poor, they're also eerily quiescent, as if their star-making machinery stalled long ago. Chemical analysis reveals ancient stellar populations with almost no young blue stars, suggesting their gas vanished early in cosmic history. Did something suppress their star formation before they could build up a richer interstellar medium? Or did they form under special conditions, emerging from primordial gas clouds already stretched thin? One provocative idea suggests these galaxies are failed giant structures that began with ample dark matter, but lost it through cosmic collisions or exotic particle interactions. Others argue they're more like cosmic fossils, relics of an era when gas was less concentrated and galaxies formed differently. Whatever the truth, they force us to rethink how galaxies assemble and evolve. Because if the interstellar medium can vanish so completely from these sprawling giants, our models of galactic growth might be missing a fundamental piece. What's tantalizing is how these ghostly galaxies mirror and contrast with their brighter cousins. Normal galaxies thrive on equilibrium, their interstellar medium constantly replenished by stellar winds and supernova debris. But ultra-diffuse galaxies seem locked in stasis, their gas lost to mechanisms we've yet to fully map. Studying them isn't just about solving a curiosity, it's a window into the delicate balance that shapes all galaxies, ours included. And until we understand why these cosmic wraiths are so empty, we can't fully grasp the rules that govern the universe's grandest structures. One of the most electrifying enigmas in modern astronomy arrives in bursts, flashes of radio energy so powerful they outshine entire galaxies, yet so brief they vanish in milliseconds. Fast radio bursts, or FRB, have puzzled scientists since their discovery in 2007, appearing without warning from all corners of the cosmos. But here's where it gets even stranger. These fleeting signals might hold the key to mapping the interstellar medium's most elusive pockets of matter, while simultaneously defying every explanation we throw at them. The first clue lies in how these pulses travel. As an FRB races through space, it doesn't move in a straight line. It interacts with the ionized plasma of the interstellar medium, slowing down slightly at different wavelengths. This effect, called dispersion, causes higher frequency waves to arrive slightly earlier than lower ones, like runners crossing a finish line at staggered times. By measuring this delay, astronomers can calculate how much material the burst has passed through, effectively turning FRBs into cosmic scales for weighing the unseen. Already, they've revealed vast reservoirs of ionized gas between galaxies, matter so diffuse it's invisible to other telescopes, but the plot twist: some FRBs repeat. Unlike one-off bursts that scream and vanish, a handful of sources fire off multiple signals, sometimes randomly, sometimes in eerie, predictable patterns. Take FRB 1219, a repeater in a dwarf galaxy 3 billion light-years away. It cycles through active phases and lulls, flashing like a malfunctioning beacon with no obvious cause. Even stranger, some repeating bursts show downward frequency drifts, as if each subsequent pulse is sliding down a cosmic slide, losing energy in a way no known astrophysical process can fully explain. Theories abound. Magnetar's ultramagnetic neutron stars are prime suspects, their crust-quaking starquakes potentially unleashing these colossal radio screams. Yet not all repeating FRBs match Magnetar behavior, leaving room for wilder possibilities. Collapsing black holes, cosmic strings, or even whisper at alien megastructures, though most astronomers consider that a distant Plan Z. The most tantalizing idea involves interactions with the interstellar medium itself. Perhaps dense plasma clouds or turbulent magnetic fields are focusing, reflecting, or even amplifying these bursts in ways we've yet to model. What's undeniable is how FRBs are rewriting the ISM's rulebook. Each burst that passes through our galaxy carries a fingerprint of the Milky Way's own plasma, revealing structures like the ionized foam near its spiral arms. Some even hint at previously unknown filaments of warm gas threading the galactic halo. As telescopes like CHIME and FAST detect thousands more bursts, they're not just solving a cosmic mystery, they're sketching the first rough maps of the universe's hidden scaffolding. The irony is exquisite. These flashes, so brief we might miss them in a blink, are illuminating the darkest corners of the cosmos. Whether they're the death cries of exotic stars or the static of interstellar plasma itself, FRBs remind us, sometimes the universe's loudest secrets come in the quietest pulses. And with every new detection, the Interstellar Medium's cryptic diary gets one page clearer. Carbon monoxide should be the perfect cosmic signpost wherever it lingers. Vast clouds of molecular hydrogen must surely follow. For decades, astronomers have relied on this logic, using CO as a tracer to map the universe's hidden reservoirs of star-forming gas. But the interstellar medium loves a good plot twist. Scans reveal vast stretches where hydrogen thrives while carbon monoxide is conspicuously absent, as if the universe has entire gas clouds hiding in plain sight. Welcome to the enigma of CO, dark molecular gas. This invisible fuel makes up a staggering chunk of the interstellar medium, perhaps as much as 30% of all molecular hydrogen. Unlike the dense, cold clouds where CO forms readily, these shadowy regions exist in a Goldilocks zone, too warm for carbon monoxide to stabilize, yet too diffuse for traditional hydrogen emission lines to stand out. Detecting them is like trying to spot fog in a moonless night. You know it's there because it dims the stars behind it, but you can't see its edges or measure its depth. So how do we track something so elusive? Astronomers have turned to cosmic detective tools like ultraviolet absorption studies. When light from distant stars passes through these gas pockets, hydrogen molecules absorb specific UV wavelengths, leaving faint fingerprints in the spectra. Another clue comes from cosmic rays, high-energy particles that collide with the hidden H2, producing gamma rays as a byproduct. These gamma-ray glows, spotted by telescopes like Fermi, reveal hydrogen's presence even when CO is nowhere to be found. The implications ripple across astrophysics. If we've underestimated the amount of molecular gas due to CO's blind spots, entire models of star formation may need recalibrating. Galaxies could be far richer in star-making fuel than we thought, rewriting timelines for cosmic evolution. Even more intriguing, this dark gas might be where complex organic molecules quietly assemble, shielded from the radiation that destroys them in more exposed regions. But the biggest puzzle remains: why does CO fail in these environments? The answer might lie in chemistry's fine print. Carbon monoxide forms when free carbon and oxygen atoms meet on dust grains, but in diffuse clouds, these atoms rarely stick together long enough to bond. Ultraviolet radiation from nearby stars can also tear CO apart faster than it forms, leaving hydrogen to dominate. It's a cosmic balancing act, one that forces us to rethink our reliance on chemical tracers and admit how much of the universe's fuel supply we've been missing. What's clear is this: the interstellar medium doesn't play by our textbook rules, and until we decode the full story of CO dark gas, we're essentially mapping a forest by counting only the tallest trees, unaware of the vast undergrowth hidden beneath. Some cosmic clouds don't just shimmer, they erupt without warning, flickering to life like matches struck in the dark. These are the interstellar flares, sudden brightenings in nebulae that defy the slow, predictable rhythms of star formation. Take the Carina Nebula's Mystic Mountain, a towering pillar of gas where sections unpredictably ignite, glowing hundreds of times brighter before fading back into obscurity. It's as if the cosmos itself is playing with a dimmer switch, and we're only just beginning to glimpse the hand behind it. What could trigger such violent outbursts? One leading suspect lurks within the clouds themselves, protostars, those embryonic stars still wrapped in their dusty cocoons. As these young stars gather mass, their gravitational tantrums might send shockwaves rippling through surrounding gas, heating it to sudden incandescence. Imagine a toddler thrashing in a pool. The water's surface erupts unpredictably, mirroring how a protostar's fits could set entire swaths of nebula alight. But here's the puzzle. Some flaring regions show no trace of embedded protostars, leaving astronomers scanning for alternative culprits. That's where magnetic reconnection enters a process so energetic it powers solar flares. When tangled magnetic field lines snap and realign, they release torrents of energy like rubber bands stretched too far and suddenly cut. In the interstellar medium's chaotic plasma, this could spark runaway heating, explaining why certain gas pockets flash without stellar input. Recent simulations suggest these magnetic fireworks might even cascade, setting off chain reactions that illuminate entire nebula complexes. Yet without direct measurements of the fields themselves, the theory remains tantalizingly unproven. Even stranger are the flares that leave no trace. Some nebulae brighten dramatically, then settle back into their original state as if nothing happened. No lingering heat, no altered chemistry. It's akin to a room lighting up momentarily, then returning to darkness without a scorch mark or a switched-on bulb. Could these be light echoes where radiation from a distant, unseen event reverberates through the gas-like sound in a canyon? Or perhaps something more exotic is at work, like quantum tunneling of energy through dense dust lanes. The stakes are higher than mere curiosity. These flares aren't just cosmic spectacles, they're potential game changers for how we understand energy transfer in the interstellar medium. If magnetic reconnection dominates, it implies a universe where invisible forces orchestrate light shows across light years. If protostars are the primary actors, it suggests even young stars wield far more influence than we've accounted for. And if the answer lies somewhere else entirely, well, that's the thrill of the hunt. With every unexplained flicker in the dark, the interstellar medium reminds us there's more to its story than we've yet uncovered. Hidden in the static of the cosmos, a whisper from the dawn of time finally reached our telescope's helium hydride, or He+, the universe's first molecule. For decades, this simple combination of helium and a hydrogen ion existed only in theory, a ghost from chemistry's infancy when the cosmos was a scorching soup of raw elements. Then, in 2019, astronomers spotted its faint fingerprint in a planetary nebula, confirming its existence at last, but the celebration turned to confusion almost immediately. If this molecule is a relic of the Big Bang, why is it so vanishingly rare? The answer could rewrite what we know about the universe's chemical origins. At first glance, helium hydride should be everywhere. In the early universe's searing heat, only the simplest bonds could survive, and He+ was the obvious first contender. Helium, the universe's second most abundant element, pairing with ionized hydrogen, the most abundant. As the cosmos expanded and cooled, these molecules were supposed to pave the way for more complex chemistry, acting as cosmic stepping stones. Yet somehow, they've managed to evade detection for nearly 14 billion years. The few instances we've found exist in violent, improbable environments, like the turbulent outskirts of dying stars, places far removed from the primordial conditions where they should thrive. One explanation lies in their fragility. Helium, the reluctant participant in chemical reactions, clings to its electrons with unmatched tenacity. Even when forced into a bond with hydrogen, the slightest nudge from radiation or collisions can tear them apart. In the modern universe, where UV light and cosmic rays flood every corner, He+ barely has a chance to form before it's shredded back into its components. But that doesn't fully account for its scarcity in shielded regions, like dense molecular clouds where other fragile molecules flourish. Some simulations suggest the early universe's chemistry might have skipped He+ entirely, with hydrogen molecules forming directly through unconventional pathways like three-atom collisions that bypassed helium's involvement altogether. Even stranger is the role of dust. In planetary nebulae where He was finally detected, dust grains might act as cosmic catalysts, providing surfaces where helium and hydrogen ions can meet safely. But if dust is the key, it introduces a chicken and egg paradox. Dust itself requires heavier elements forged in stars, meaning the first He molecules would have had to form without it. Could there have been a brief, invisible epoch where He was abundant, only for it to vanish as dust took over chemistry's heavy lifting? Or does its elusiveness hint at gaps in our understanding of how matter behaved in those first turbulent millennia? The stakes are higher than a simple accounting exercise. If He+'s scarcity is real, it implies the early universe's chemical forge operated under rules we've yet to decipher, rules that might have shaped everything that followed. Did its absence slow the birth of the first molecules, delaying the cooling of gas clouds and the ignition of the earliest stars? Or did nature find workarounds we're only beginning to trace? Every undetected He+ molecule is a silent witness to those primordial moments, and until we understand why they're hiding, a chapter of cosmic history remains half-written. For now, the hunt continues, with radio telescopes scanning the void for whispers of a bond that started it all. Galaxies breathe not in gulps of air, but in great, slow cycles of expulsion and return. Supernova, those catastrophic stellar explosions, act as cosmic bellows, blasting gas out into the halos of galaxies at millions of miles per hour. This material doesn't simply vanish into the void. It arcs high above the galactic disk, cools, and eventually comes raining back down in what astronomers poetically call galactic fountains. But there's a problem. When scientists simulate this process, the numbers don't add up. The gas should recycle efficiently, fueling new generations of stars. Instead, observations show it's vanishing somewhere along the way, as if the universe has sprung a leak. Take the Milky Way. Our galaxy's supernova launch about 10 solar masses of gas into the halo every year, enough to refill its star-forming reservoirs over time. Yet when researchers track this outflow's journey, only a fraction makes it back. Some of the gas gets so hot during its ascent that it escapes the galaxy's gravity entirely, streaming away as part of the galactic wind. Other portions seem to stall in the halo, forming enormous, diffuse clouds that glow faintly in X-rays. These clouds, detected by observatories like Chandra, hover for millions of years, neither falling nor fleeing, like water caught in midair during a slow-motion splash. The real conundrum lies in the cooling rates. For fountain gas to return, it must shed energy, condensing until gravity pulls it homeward. But our models suggest this cooling should happen far faster than what we observe. Magnetic fields might play a role, acting as cosmic insulation to slow the process down. Turbulence could also stir the gas, keeping it hot longer, like a spoon swirling a steaming cup. Yet even these tweaks don't fully explain the discrepancy. Some hidden mechanism, perhaps interactions with dark matter or unseen plasma waves, could be throwing a wrench into the works. Then there's the wild card, cosmic rays. These high-energy particles, accelerated by supernova shocks, might inject extra heat into the outflows or even propel them further like invisible sails. Recent simulations that include cosmic ray pressure show gas fountains behaving more like observations, with material lingering in the halo before eventually trickling back. But this introduces another puzzle. Why do some galaxies show robust recycling while others, like quiescent ellipticals, seem to hemorrhage gas entirely? The stakes are cosmic. If galaxies lose too much of their fountain material, they starve themselves of the fuel needed to birth new stars. This could explain why some galaxies age into retirement prematurely, their stellar factories shutting down far earlier than expected. On the flip side, if the recycling is more efficient than we've accounted for, it might mean galaxies can sustain star formation longer, altering our timelines for cosmic evolution. What's clear is that galactic fountains aren't just beautiful metaphors, they're critical plumbing in the universe's ecosystem. And until we find where the pipes are clogged or broken, we're missing a fundamental chapter in the story of how galaxies live, die, and replenish themselves across eons. The answer might be hiding in plain sight, carried on those slow rains of gas falling silently through the dark. The universe hums, not with sound, but with strange, unexplained microwaves that ripple through the interstellar medium like a cosmic static. This is anomalous microwave emission, or AIM, a phenomenon first detected in the 1990s when astronomers noticed extra microwave radiation coming from dust clouds, radiation that shouldn't exist based on known physics. The culprit, tiny specks of dust spinning millions of times per second, emitting microwaves like microscopic radio transmitters. But what kind of dust could possibly behave this way? The answer has split scientists into rival camps, each armed with compelling yet conflicting evidence. At the heart of the debate are two competing theories. The first points to polycyclic aromatic hydrocarbons, or PAR-flat, carbon-based molecules that resemble microscopic flakes of soot. These molecules are abundant in space, and when struck by starlight, they can start spinning rapidly, emitting microwaves as they twirl. Supporters of this idea note that PAHs are found everywhere AIM is detected, like cosmic breadcrumbs leading to a solution. But there's a catch. Lab experiments struggle to make PAHs spin fast enough to match the observed signals. It's like trying to explain a hurricane with a desk fan. The scale just doesn't add up. The second theory throws magnetism into the mix. Some researchers argue the microwaves come from ultra-small grains of iron or magnetite, their spins locked in place by magnetic fields. When these grains jostle in the interstellar medium, their magnetic poles wobble, releasing microwave energy in the process. This would neatly explain the signal's strength and distribution, especially in regions where PAHs are scarce. Yet even here, lab tests fall short. No one has been able to reproduce the exact microwave signatures using these magnetic grains, leaving a frustrating gap between theory and observation. What makes AIM even more puzzling is its uncanny correlation with far-infrared light. Wherever these microwaves appear, they're almost always accompanied by a specific wavelength of infrared radiation, a clue that the dust grains might be responding to starlight in unexpected ways. Some models suggest a two-step process. Photons bump into the grains, setting them spinning, and then, as they slow down, they release energy as microwaves. But without direct lab confirmation, these ideas remain elegant guesses rather than proven facts. Perhaps the most tantalizing possibility is that we're dealing with something entirely new, an unknown class of nanoparticles with properties that bridge the gap between PAHs and magnetic grains. Could interstellar chemistry be cooking up exotic hybrids like carbon-wrapped magnetic crystals or fractal dust structures that defy our current categories? Until we can scoop up actual samples or replicate the conditions of deep space in a lab, AIM will keep its secrets close. What's certain is this: these microwaves aren't just background noise. They're a fingerprint of the interstellar medium's hidden architecture, a reminder that even the tiniest particles can rewrite the rules when we're not looking. And with every new observation, the static of the cosmos grows louder, begging us to listen closer. Rising like colossal smokestacks from the fiery forges of star formation, the interstellar medium's chimneys are among the most dramatic structures in the galaxy, towering conduits that funnel superheated gas straight out of the galactic disk and into the halo. Stretching hundreds of light years tall, these chimneys aren't built of brick or metal, but of pure energy, sculpted by the combined fury of supernova and stellar winds. Picture a volcanic eruption frozen mid-blast, its plume arrested in time, and you'll start to grasp their scale. But what's truly baffling isn't just their size, it's the way they blur the line between creation and destruction. simultaneously feeding the galaxy's growth while bleeding its lifeblood into the void. The discovery of these chimneys rewrote our understanding of galactic ecosystems. For decades, astronomers assumed gas circulated lazily through galaxies like steam rising from a cup of tea. But observations from X-ray and radio telescopes revealed something far more violent: chimneys acting as escape routes for cosmic rays and ionized gas, punching through the disk's magnetic field lines like bullets through tissue paper. In the Milky Way's Fermi Bubbles, we might even be seeing the aftermath of such structures, their faded outlines hinting at ancient eruptions that once reached halfway to intergalactic space. The debate over what powers these chimneys splits astrophysics into two camps. On one side, proponents of stellar feedback argue that the collective might of supernova, dozens exploding in concert within star-forming regions, can launch these geysers. Simulations show how overlapping blast waves create superbubbles that stretch and rupture the disk, like bubbles swelling beneath the surface of a boiling pot. Yet skeptics point out that some chimneys appear in regions with surprisingly modest star formation, their energy output defying the stellar feedback model. That's where active galactic nuclei, or AN, enter the picture. Could the supermassive black holes at galactic centers, flickering to life during feeding frenzies, be the true architects? When these monsters awaken, their relativistic jets might drill precisely the kind of channels we observe, injecting energy from above rather than below. What's mesmerizing is how chimneys interact with cosmic rays. These high-energy particles, normally trapped by the galaxy's magnetic fields, might use chimneys as escape hatches, surfing the outflowing gas into intergalactic space. Observations of gamma-ray glow along chimney walls support this idea, like finding scorch marks near a muzzle. But here's the twist: some chimneys appear to funnel rays back into the disk, their magnetic fields acting as cosmic slides that return particles to the galactic fray. This duality makes them both exits and highways, shaping where and how cosmic rays travel. The implications ripple far beyond our galaxy. If chimneys are common features, they could explain why some galaxies quench prematurely, their star-forming gas ejected before it can coalesce into new suns. They might also serve as bridges, ferrying enriched material from galactic disks to halos, where it could someday rain back down or be lost forever. For now, these towering conduits remain a testament to the interstellar medium's hidden dynamism, reminding us that even in the vast quiet between stars, forces are at work that can reshape entire galaxies. Among all the elements forged in the fires of the Big Bang, lithium should be one of the easiest to account for: 3 protons, 4 neutrons, and a straightforward creation story. Yet when astronomers tally its presence in the interstellar medium, the numbers come up shockingly short. Stars, gas clouds, and even ancient stellar atmospheres contain only a fraction of the lithium predicted by cosmic nucleosynthesis models. It's as if the universe misplaced an entire atomic ingredient, and the interstellar medium might be hiding the crime scene. This isn't just a minor accounting error. According to our best models of the early universe, lithium-7, the heavier, stable isotope, should be about 3 times more abundant than what we actually observe. Even more baffling, the discrepancy isn't uniform. Some of the oldest stars in the Milky Way, relics from near the dawn of time, show some primordial lithium, but still far less than expected. Meanwhile, younger stars and the diffuse ISM display even lower levels, suggesting something has been actively destroying lithium across cosmic history. The question isn't just where did it go, but also how is it vanishing faster than we can explain. One clue lies in stellar furnaces. When lithium encounters temperatures above 2 million Kelvin, common in stellar interiors, it fuses into heavier elements like helium. This explains why stars deplete their own lithium over time, but it can't account for the shortage in cold interstellar gas, where temperatures are too low for such reactions. Could cosmic rays be the culprits? High-energy particles smashing into lithium atoms in the ISM might shatter them, but calculations show this process is too inefficient to explain the scale of the deficit. Then there's the wild card, unknown chemistry. Laboratory experiments reveal that lithium can bind with dust grains or form molecules like lithium hydride in cold, dense clouds. If these compounds are more common than assumed, they might escape detection by traditional telescopes tuned to atomic lithium's signature wavelengths. Imagine the ISM as a vast warehouse where lithium isn't missing. It's just repackaged in boxes we haven't learned to open yet. The problem, even these hiding places can't fully reconcile the disparity. The most tantalizing possibility involves physics beyond our current models. What if lithium is being destroyed by hypothetical particles or rare nuclear reactions we've yet to discover? Some theorists propose that certain dark matter interactions could break apart lithium nuclei, while others speculate about fluctuations in the fundamental constants of nature during the universe's first minutes. These ideas border on the speculative, but the lithium problem is stubborn enough to warrant them. Every unresolved lithium atom is a silent witness to gaps in our understanding of nucleosynthesis, of stellar evolution, of the ISM's hidden chemistry. Until we solve it, we're not just missing an element, we're missing a piece of the universe's foundational blueprint. And somewhere in the dark between the stars, the answer might be floating just out of reach. Some of the universe's most spectacular voids aren't empty at all, they're superbubbles, colossal cavities blown by the combined fury of stellar winds and supernova explosions. These cosmic bubbles should be chaos incarnate, their edges rippling with shockwaves as they expand through the interstellar medium. Yet when astronomers peer into some of these structures, they find eerie silence where there should be cosmic fireworks, missing shock signatures that defy every expectation. It's as if the universe has built a series of invisible baffles, muffling the aftermath of stellar violence in ways we can't yet explain. Take the Orion Eridanus superbubble, a vast cavity spanning over 1,000 light-years near our own stellar neighborhood. Models predict its edges should glow with X-rays and radio emissions, the telltale signs of gas heated to millions of degrees by relentless shocks. Instead, large swaths of its shell appear strangely muted, like a fireworks display where half the explosions fail to ignite. One explanation points to hidden cooling mechanisms. Perhaps clouds of colder gas embedded in the bubble's walls act like cosmic sponges, soaking up energy before it can radiate as expected. Recent observations reveal clumps of molecular gas lurking along these boundaries, their presence disrupting shock fronts before they fully develop, but cooling alone doesn't solve the puzzle. Some superbubbles, like the one in the Large Magellanic Clouds N44 region, show suppression even where cooling seems insufficient. That's where magnetic fields enter the fray. Simulations suggest tangled field lines could act like internal scaffolding, stabilizing the bubble's expansion and preventing the runaway turbulence that typically generates observable shocks. Picture trying to inflate a balloon inside a mesh cage. The structure expands, but the cage keeps it from popping violently. If confirmed, this would mean magnetic fields play a far more dynamic role in shaping interstellar structures than we've assumed, silently orchestrating the chaos of stellar feedback. The strangest twist comes from superbubbles that appear to be leaking. In the galaxy NGC 3792, X-ray telescopes have spotted faint tendrils of gas extending beyond the bubble's expected boundary, as if shock energy is bleeding away through unseen channels. One provocative theory suggests cosmic rays are to blame. These high-energy particles might carve escape routes through the bubble's walls, siphoning energy into the wider interstellar medium before it can manifest as detectable shocks. It's a cosmic version of a pressure relief valve, one that could rewrite how we model the life cycle of these colossal structures. What's at stake goes beyond astrophysical curiosity. Superbubbles are the engines of galactic ecology, redistributing energy and heavy elements across star-forming regions. If their energy vanishes into hidden pathways, our understanding of how galaxies evolve, how they regulate star formation and recycle material, might be missing a fundamental piece. For now, these eerily quiet cavities stand as cosmic riddles, their silence louder than any shockwave could ever be. The interstellar medium shouldn't be this chaotic. Gas clouds racing at supersonic speeds faster than the speed of sound in their own environment should crash, dissipate, and slow to a murmur almost instantly. Yet when astronomers measure these turbulent motions, they linger far longer than physics textbooks say they should, like a hurricane that refuses to die even after crossing an entire continent. This turbulence puzzle isn't just a quirk, it's a fundamental crack in our understanding of how energy moves through the cosmos. The mystery starts with scale. Turbulence in the ISM isn't random, it follows fractal patterns, repeating its frenzied structure whether you zoom in on a light year or a parsec. Imagine stirring cream into coffee and watching the swirls maintain their intricate shapes no matter how much you dilute the mixture. That self-similarity suggests something deeper is at work, a hidden mechanism constantly replenishing the chaos. But what supernova are the usual suspects? These stellar explosions blast shockwaves through surrounding gas, stirring it like a spoon in a cosmic cup. Simulations show a single supernova can inject enough energy to keep a region churning for millennia. Yet when astronomers tally up the numbers, there's a mismatch. The observed turbulence exceeds what supernova alone can explain, especially in quieter galactic suburbs where explosions are rare. That's led some researchers to suspect galactic rotation itself might be the unseen agitator. As spiral arms shear through gas clouds, their differential rotation, faster near the galaxy's core, slower at the edges, could stretch and twist the interstellar medium into sustained turmoil like taffy pulled in opposite directions. But here's where the plot thickens. Even these combined forces struggle to account for the sheer persistence of the turbulence. Enter magnetic fields, those invisible threads woven through the ISM. They might act as cosmic shock absorbers, converting kinetic energy into magnetic waves that reverberate through the gas, prolonging the chaos like an echo in a canyon. Some models even suggest that turbulence could be self-sustaining at certain scales, with larger eddies fragmenting into smaller ones in an endless cascade, a process known as turbulent dissipation. The implications ripple far beyond academic curiosity. Turbulence dictates how gas collapses into stars, how cosmic rays propagate, even how galaxies evolve. Too much turbulence and star-forming clouds rip apart before they can ignite. Too little and gas stagnates, unable to shed the heat that prevents gravitational collapse. The ISM's relentless churning might be the universe's way of walking a tightrope between creation and stagnation. For now, the puzzle remains unsolved, a reminder that even in the apparent chaos of the cosmos, there's an order we're only beginning to trace. And somewhere in that maelstrom of supersonic gas, the answer is swirling just out of reach. Oxygen should be one of the easiest elements to spot in the interstellar medium. After all, it's the universe's third most abundant atom, forged in the hearts of stars and scattered across the cosmos by supernova. Yet when astronomers search for it in the space between stars, something doesn't add up. The expected reservoirs of free oxygen gas, the kind that should glow in spectroscopic observations, are conspicuously thin, as if the galaxy has quietly tucked away one of its most vital ingredients. This isn't just a minor accounting error, it's a full-blown cosmic whodunit, and the suspects range from stardust to invisible ionic traps. One theory points to interstellar dust as the ultimate oxygen thief. Tiny grains, many no larger than smoke particles, could be locking oxygen away in solid form, trapping it inside minerals like silicates or metal oxides. Picture a sponge soaking up water until it's saturated. These dust grains might be doing the same with oxygen, leaving little left to detect in its gaseous state. Supporting this idea, infrared telescopes have spotted hints of oxygen-rich compounds clinging to dust in regions like the Taurus molecular cloud. But here's the catch: even accounting for these solid hiding places, the numbers still fall short. If dust is the culprit, it's an improbably efficient one, hoarding oxygen at a rate that defies our understanding of cosmic chemistry. That's where atomic physics throws a curveball. Oxygen doesn't always behave like we expect in the harsh environment of space. In the diffuse, ionized gas of the interstellar medium, oxygen atoms can lose electrons, becoming highly reactive ions that don't emit light at the wavelengths we typically monitor. These dark ionic states like O++ or O3+ might be lurking everywhere, invisible to our telescopes but dominating the oxygen budget. It's like searching for a person by scanning for their shadow, only to realize they're standing right in front of you, perfectly backlit. Recent advances in ultraviolet spectroscopy have begun peeling back this veil, revealing faint absorption lines that hint at these elusive ion populations. Yet even these detections can't fully close the gap, leaving a stubborn fraction of oxygen still unaccounted for. Then there's the wild card, molecular oxygen, or O2. On Earth, it's the breath of life, but in space, it's maddeningly elusive. Despite decades of searching, astronomers have spotted it in only a handful of regions, like the Rho-Ophiuchi cloud. The irony is thick oxygen molecules, which should form readily in the cold depths of molecular clouds, seem to vanish almost as quickly as they appear. Some researchers blame cosmic rays, which might shatter O2 into atomic fragments before it can accumulate. Others speculate that oxygen binds with hydrogen to form water ice on dust grains, hiding in a form that's nearly impossible to detect remotely. The stakes are higher than they might seem. Oxygen isn't just a passive bystander in the interstellar medium. It's a key player in cooling gas clouds, enabling them to collapse into stars. If large amounts are locked away or invisible, our models of star formation might be missing a critical variable. Even more tantalizing is oxygen's role in prebiotic chemistry, the cosmic groundwork for life. Could its strange disappearance hint at unseen pathways for molecule formation, ones that operate in the shadows of our observations? For now, the case of the missing oxygen remains wide open. Every new telescope, from the James Webb Space Telescope to upcoming X-ray observatories, brings us closer to cracking it. But until we do, the interstellar medium keeps its secrets well hidden, reminding us that even the most abundant things in the universe can slip through our fingers when we're not looking closely enough. Racing through the galactic halo at hundreds of kilometers per second, high-velocity clouds are the interstellar medium's rogue travelers, massive streams of gas hurtling fast enough to cross the Milky Way in a cosmic blink. These aren't the placid, star-forming nebulae we're accustomed to. They're streaks of primordial matter, some stretching tens of thousands of light years, their origins debated as fiercely as their ultimate fate. What makes them truly enigmatic isn't just their speed, but their stubborn refusal to fit neatly into any single narrative. Are they remnants of the galaxy's violent birth, or intergalactic hitchhikers captured from the void? The answer might lie in their peculiar chemistry, a fingerprint as telling as it is elusive. The first clue comes from their metal content, or rather, the lack of it. Unlike the Milky Way's churning disk, where supernovae have peppered gas with heavy elements for billions of years, high-velocity clouds are strikingly pristine. Their metallicity, the fraction of elements heavier than hydrogen and helium, can be as low as 10% of the Sun's, a purity that points to origins untouched by stellar alchemy. This scarcity of metals suggests two possibilities. Either these clouds are ancient relics, leftover building blocks from the galaxy's formation that never collapsed into stars, or they're interlopers, fresh arrivals from the metal-poor depths of intergalactic space. The relic theory paints a picture of the Milky Way as a cosmic hoarder, surrounded by the crumbs of its own assembly. Simulations show that when galaxies form, not all gas settles into the disk. Some get strung along in vast, looping filaments, cooling slowly over eons. These threads might condense into the high-velocity clouds we observe today, their momentum preserved like a fossil record of the galaxy's turbulent youth. Supporting this, some clouds orbit in predictable patterns, their trajectories tracing the ghostly outlines of long-vanished rivers of primordial gas. But not all clouds follow the rules. The Smith Cloud, a massive gas stream hurtling toward the Milky Way's disk at nearly 300 kilometers per second, defies easy classification. Its trajectory suggests it's on a return trip, having already punched through the galactic plane millions of years ago. Even stranger, its leading edge glows faintly with ionized gas, as if the cloud is being sandblasted by the galaxy's own halo. If this is a relic, it's one that's been dramatically reshaped by its environment, or perhaps it's something else entirely. That's where the intruder hypothesis takes hold. Some high-velocity clouds might not belong to the Milky Way at all. They could be shreds torn from dwarf galaxies or even splinters of the cosmic web itself. The Magellanic Stream, a colossal ribbon of gas trailing the Milky Way's satellite galaxies, is a prime example, a structure so vast it wraps around the entire sky. Its low metallicity matches the small Magellanic Cloud, suggesting it was stripped away by tidal forces during a close encounter. Other clouds, like Complex H, move too fast to be bound to the Milky Way, their velocities hinting at a fleeting passage through our celestial neighborhood. The stakes are cosmic. If high-velocity clouds are galactic leftovers, they're a living museum of the universe's raw materials, offering a glimpse into conditions before the first stars ignited. If they're intergalactic visitors, they represent something even more profound: the Milky Way's ongoing growth through cannibalism, a slow feast of gas that fuels future star birth. Either way, their journey isn't over. Many are destined to collide with the galactic disk, their gas raining down to replenish the interstellar medium and spark new generations of stars. Yet the mystery deepens with every observation. Recent studies have spotted clouds with puzzlingly mixed chemistries, patches of higher metallicity embedded within otherwise pristine gas like swirls in marble. Could these be the result of collisions between different populations, or evidence of hidden stellar nurseries in the halo? For now, the clouds keep their secrets, racing silently through the dark, their origins as fluid as the gas they're made of. One thing's certain: in their speed and simplicity, they hold chapters of the galaxy's story we've only begun to read. The interstellar medium isn't just a passive backdrop for celestial drama. It's a stage where invisible forces occasionally flare into view, and few phenomena are as enigmatic as the dark gamma-ray sources. These are bursts of the universe's most energetic light, radiating from regions that otherwise appear empty, their origins masked by the very gas and dust they illuminate. Unlike pulsars or active galaxies, which announce themselves with predictable rhythms, these gamma-ray hotspots flicker unpredictably, their brilliance untethered to any visible cosmic landmark. It's as if the interstellar medium itself is generating these outbursts, channeling energy through mechanisms we've yet to decipher. One prime suspect: hidden pulsars, the spinning corpses of dead stars, their beams of radiation sweeping across space like cosmic lighthouses. Normally, we'd spot these objects by their rhythmic pulses or the glowing nebulae they power. But some might be obscured by dense curtains of interstellar dust, their visible light entirely swallowed, leaving only the most penetrating gamma rays to escape. Alternatively, they could be black widow pulsars, those that have vaporized their companion stars with relentless radiation, leaving behind isolated remnants too faint to detect except in these fleeting high-energy flashes. Yet even this explanation falls short for sources that show no periodicity, no telltale pulse to betray their identity. Then there's the darker possibility, annihilation. If dark matter consists of weakly interacting massive particles, or WIMP, these elusive entities could be colliding in the depths of interstellar clouds, their mutual destruction converting mass into pure energy. Certain regions like the galactic center or the dense cores of molecular clouds should act as dark matter gathering grounds, their gravitational pull concentrating these particles until collisions become inevitable. The gamma rays we detect could be the final flashes of these invisible interactions, a faint echo of the universe's hidden architecture. But here's the catch: the energy signatures don't always match theoretical predictions. Some dark gamma ray sources glow too brightly or in patterns that defy annihilation models, leaving astronomers to wonder if they're seeing dark matter's handiwork or something entirely unexpected. The wild card in this cosmic deck, turbulence. The interstellar medium is a seething ocean of magnetized gas, where shock waves from supernova and stellar winds collide at velocities high enough to accelerate particles to extreme energies. In these chaotic zones, protons and electrons might slam into each other with such force that they emit gamma rays as a byproduct. It's the same process that powers the diffuse glow of the Milky Way's gamma-ray fog. But in these mysterious hotspots, the effect could be amplified to dazzling extremes. Imagine a storm at sea where waves crashing together send spray high into the air. Only here, the spray is gamma radiation, and the waves are vast currents of ionized gas. What makes these dark sources so compelling isn't just their obscurity, but their defiance of categorization. Some align with known supernova remnants, their gamma rays hinting at unseen particle accelerators buried in the wreckage. Others drift in the voids between stars, their emissions too sustained for a single catastrophic event. And a few even seem to wander, their positions shifting slightly over years, as if tied to some unseen, moving structure, perhaps a rogue black hole or a neutron star adrift in the dark. The stakes cut to the heart of astrophysics. If pulsars are responsible, we're missing a crucial population of stellar remnants hiding in plain sight. If dark matter is the culprit, it would be the closest we've come to touching this shadowy substance. And if turbulence alone can generate such brilliance, it would rewrite our understanding of how energy propagates through the galaxy. For now, the interstellar medium keeps its secrets, flashing these gamma-ray riddles like a cosmic Morse code, one we're still learning to read. The interstellar medium should be a textbook example of cosmic thermodynamics: hot gas glowing in X-rays, cold gas pooling in molecular clouds, and everything in between neatly following the laws of physics. But when astronomers compare theoretical temperature maps to real observations, the numbers refuse to line up. Some regions blaze hotter than models predict, while others remain stubbornly frosty against all expectations. This mismatch isn't just a minor calibration error. It's a fundamental rift in how we understand energy flows through the universe, and nowhere is the discrepancy more glaring than in galaxy clusters, where the so-called cooling flow problem has upended decades of assumptions. Galaxy clusters, the universe's largest gravitationally bound structures, should be cosmic cauldrons of cooling gas, packed with superheated plasma at tens of millions of degrees. This gas ought to radiate energy away as X-rays, gradually chilling until it drips toward the cluster's core like condensation on a windowpane. This cooling flow should fuel star formation, feeding the cluster's central galaxies with a steady rain of fresh material. Yet when telescopes like Chandra and XMM Newton peered into these clusters, they found something startling: the gas isn't cooling as expected. In fact, below certain temperatures, the cooling process seems to stall entirely, as if the universe flipped a hidden switch. One explanation points to active galactic nuclei, the supermassive black holes lurking at the hearts of these clusters. As gas cools and drifts inward, it might trigger outbursts from the black hole, sending jets of plasma roaring back into the surrounding medium. These jets could reheat the gas, creating a feedback loop that prevents runaway cooling. Picture a thermostat gone haywire, swinging between blast furnace heat and near absolute zero, never settling into equilibrium. Supporting this idea, X-ray images reveal cavities carved by AGN jets, their edges shimmering with shock-heated gas. But the mystery deepens when we zoom in. Some clusters show no signs of recent AGN activity, yet their gas still refuses to cool below a critical threshold. Then there's the puzzle of the missing intermediate temperature gas. Thermodynamics dictates that cooling should happen gradually, with gas passing through distinct thermal phases as it loses energy. Yet observations reveal a curious gap, plenty of scorching hot plasma and frigid molecular clouds, but surprisingly little of the warm gas that ought to bridge them. It's as if the interstellar medium has a preference for extremes, skipping the middle ground entirely. Turbulence might hold the key. Chaotic motions in the plasma could mix hot and cold gas directly, like pouring boiling water into ice and getting lukewarm steam without ever seeing liquid in between. The implications ripple beyond galaxy clusters. Similar mismatches plague our Milky Way's own interstellar medium, where certain regions resist heating or cooling as predicted. Take the galactic center's bizarrely cold molecular clouds, which hover near absolute zero despite being bathed in radiation from nearby stars and black holes. Or the local bubble, a cavity of shockingly uniform temperature around our solar system, its origins still debated. These anomalies suggest a universal principle at work, one where unknown processes regulate thermal energy in ways our models fail to capture. What's tantalizing is how this ties into another cosmic conundrum, entropy. In theory, the universe should always trend toward disorder, with energy dispersing evenly over time. Yet the interstellar medium's temperature map resembles a patchwork quilt, with pockets of high and low entropy coexisting like oil and water. Could magnetic fields be trapping heat in some regions while accelerating cooling in others? Or are we seeing the fingerprints of dark matter, its gravitational influence subtly altering how gas dissipates energy? For now, the cooling flow problem stands as a humbling reminder that the universe's thermostat is far more intricate than we've imagined. Every mismatch between prediction and observation isn't just a gap in our knowledge, it's a clue waiting to reveal the hidden mechanisms that shape the cosmos. And until we crack the code, the interstellar medium's temperature map remains a cryptic ledger, its entries written in a language we're still learning to read. In the swirling dust of the interstellar medium, astronomers once thought they'd glimpsed the universe's birth certificate, a faint signal imprinted during the Big Bang's first tremors. Known as the Bicep 2 Planck detection, this controversial finding sent shockwaves through cosmology when announced in 2014. Researchers claim to have spotted polarized light patterns in Milky Way dust, patterns that supposedly carried echoes of primordial gravitational waves from cosmic inflation. It was a discovery that promised to rewrite textbooks until it didn't. The excitement hinged on a subtle fingerprint called B-mode polarization, a specific swirled pattern in the thermal radiation left over from the universe's infancy. When the Bicep 2 team saw this signature in observations of the interstellar medium's dust clouds, they initially believed they'd uncovered vibrations from the universe's exponential expansion in its first trillionth of a second. But the celebration was premature. Later analysis by the Planck satellite revealed the signal wasn't cosmic at all. It was local contamination, the interstellar medium's own dust grains mimicking inflationary patterns through mundane magnetic alignment. What makes this phantom signal so fascinating isn't just its retraction, but what it revealed about cosmic dust's capacity for deception. The interstellar medium's dust particles, when subjected to magnetic fields, align like microscopic compass needles. As starlight scatters off these aligned grains, it polarizes in ways eerily similar to predictions for primordial inflation signals. The implications are profound. the very material we once considered background noise might hold intricate magnetic histories of its own, capable of masquerading as universe-shaking discoveries. This episode forced astrophysics into a reckoning with its tools and assumptions. Future searches for primordial magnetism must now account for the interstellar medium's confounding complexity. New techniques like multi-frequency mapping have emerged, allowing scientists to disentangle local dust effects from true cosmic signals. The upcoming CMB-S4 experiment, for instance, will scan the sky across numerous wavelengths, creating a dust thermometer to isolate contaminants with unprecedented precision. Yet the BICEP 2 saga also uncovered an unexpected silver lining. While the signal wasn't primordial, its dust polarization origins showcased the interstellar medium's hidden magnetic artistry. These aligned dust grains trace the Milky Way's magnetic skeleton in 3 dimensions, revealing previously invisible forces shaping our galactic environment. What first appeared as noise turned out to be a Rosetta Stone for decoding magnetic turbulence, star-forming regions, and even the mysterious origins of galactic magnetism itself. The greatest lesson might be one of cosmic humility. The universe often speaks in whispers, and sometimes the most tantalizing whispers come from our own celestial backyard rather than the edge of time. As next-generation telescopes continue hunting for true inflationary signals, they'll do so with hard-won wisdom. To truly hear the universe's oldest stories, we must first learn to filter out the interstellar medium's captivating but distracting murmur. The interstellar medium isn't just the space between stars, it's the universe's ultimate testing ground, a sprawling laboratory where physics gets pushed to its limits. Every wisp of gas, every grain of dust, every unexplained flicker of radiation holds clues to mysteries that defy our current understanding of reality. From the ghostly whispers of dark molecular clouds to the explosive signatures of gamma-ray bursts, the ISM doesn't just host these puzzles. It actively shapes them, presenting us with riddles that demand entirely new ways of seeing the cosmos. This relentless mystery is what drives our most ambitious telescopes forward. The James Webb Space Telescope, with its infrared eyes peeled for hidden chemistry in stellar nurseries, was designed to decode the ISM's shadowy molecular language. Meanwhile, the square-kilometer array's vast radio ears will listen for the faintest murmurs of hydrogen and cosmic rays, mapping the magnetic highways that structure the void. These aren't just instruments, they're responses to the interstellar medium's relentless challenge. Our best attempts to eavesdrop on a conversation the universe started billions of years ago. Consider how much we've already uncovered by chasing these enigmas. The hunt for missing baryons led us to the cosmic web's hidden filaments. The puzzle of anomalous microwave emission revealed nanoparticles spinning at unimaginable speeds. Even failed experiments like the BICEP 2 team's dust-confounded inflation signal taught us more about galactic magnetism than we'd learned in decades. Every dead end has been a detour to something profound, proving that in the interstellar medium, the journey toward understanding often matters more than the destination. What's thrilling is how much remains undiscovered. Future observatories will probe the ISM with resolutions sharp enough to trace the chemistry of individual dust grains, or sensitivities fine enough to catch dark matter's whisper. Perhaps we'll finally witness magnetic reconnection events that power interstellar flares, or capture the birth of helium hydride in some forgotten gas cloud. Maybe the answers lie in phenomena we haven't even named yet, processes waiting beyond the edges of our current theories. So here's the real question the interstellar medium leaves us with. What will we find when we look closer? The gas between stars has already rewritten textbooks on chemistry, thermodynamics, and even the origins of life itself. Its next revelations could upend everything from quantum physics to cosmology. Until then, we're all witnesses to this grand investigation, watching as humanity's tools and ingenuity rise to meet the universe's endless creativity. Share your favorite interstellar mystery below, because in this cosmic laboratory, the next breakthrough might be lurking in the comments of a YouTube video, waiting to spark the idea that changes everything.